All right, I guess we'll go ahead and get started. It's 6 o'clock. Tonight we want to talk about topic modeling. Then we're going to talk about sentiment analysis. Then we're going to talk about string distances. All right, so the first one is topic modeling. All right, so what we want to do, let's see, am I recording? Do I remember to hit the recording button? Yes, I'm recording. All right, so what we want to do is I have a collection of documents. That might be tweets, that might be chapters of book. This might be entire books themselves. But with our original data, we're going to have like a long vector of a document. So each entry corresponds to one document that we're working with. So now, after we convert our documents into single cell entries of that vector, and we set up our data for the purpose of string analytics, we want to see, well, what's in there? And we want to get an idea of what are the topics. All right, so our approach to this is really, what we're going to do is we're going to convert our documents to document term matrices. Remember those are matrices. They're for counts, 0, 1, 2, 3, 4. And each number indicates the number of times a term is used in the document. And then what we want to do is we're going to perform dimension reduction on the document term matrix. So now, how is this going to work out? So remember in dimension reduction, I'm going to choose a number of columns, number of fields to have left after I do the reduction. All right, so the idea that we have is that the dimension reduction aspect, the columns that are left, will hopefully correspond to a topic of interest as a group. And so then, assuming that we've made a good choice on the number of topics, what we'll do is we'll use the document term matrix reduced dimension version, and we use the individual columns to get an idea of, well, this document belongs to topic 1, this document belongs to topic 3, and so on down the list. And then we can look at each of these, look at the documents inside. After we classify them, we look and see what's inside all of the documents that are in topic 1, all the documents that correspond to topic 2, and so on. Look at their words, look at what's going on, look at their titles, and then see, hey, I think that this is an individual topic, this is an individual topic, this is an individual topic. All right, so potentially any method that we could have for dimension reduction could work. But this is going to be more similar to non-negative matrix factorization. And so in that idea, what we're doing is I'm going to find two matrices that are, when I multiply them together, I'm going to get something that's approximately, I emphasize the approximately equal to the original document term matrix. So I'm going to take the product. So let's say I choose 3 as the dimension reduction, 3 for the number of topics. Then when I do the multiplication, I'm going to have rank 1, rank 2, or rank 3 matrix that's approximately equal to the original. And so there is kind of a information loss there, but that's okay. And the matrix on the left in that product is where we're actually getting our topics from. All right, so the actual algorithm itself is a little bit different than non-negative matrix factorization. It's a little bit more tailored to what's going on. But it's okay to just think that this is the same algorithm. And so our output, what we want to do is I want to say, like, I want to figure possibly one use of this is I want to identify what are the topics of what's being talked about in these documents. Another one is I want to be able to see, like, okay, I take this document here, it comes in. I don't want to read it, but I want to know how much of it looks like it's in topic 1, how much of it is in topic 2, like how much of it is for topic 3, proportionally speaking. And, or I might want to be able to classify and just, hey, from a classification point of view, I'm going to put this in with topic 4, this one I'll put with topic 5. And so one thing is to try and find what topics there are for the collection of documents. Another one is with modeled likelihood, I could model, you know what, this document looks like it's 50% topic 1, 25% topic 2, 25% topic 3, something like that. Or I could use that same likelihood to classify each document, depending on what you're doing. Also, another thing that we could use, and this is what I've done professionally, if I have a text field in my data, I can do topic modeling to reduce that document term matrix into just a few columns and then make a prediction. So let's say I'm dealing with quality analytics and I want to predict, let's say quality analytics in a pharmaceutical setting. And I want to know is, so like in quality analytics, basically you're only handling in situations where there's already a problem. A problem has occurred, like maybe the pharmaceutical got outside of temperature range. Maybe it wasn't packaged correctly. Maybe the purification process failed, something like that. Well, something happens. They write down some notes about what happens. And then like they do this over and over and over. And then when I get the data, my goal is to try and identify, beforehand, the next time that there is a problem, is this going to be like how long is this going to take to resolve? Or is there going to be a problem with it resolving? Is this going to be require a rework? Is this going to be a severe problem? And we could use the likelihood vectors as predictor variables for that. And so this is useful in a situation where I don't want to use the entire document term matrix for the purpose of a predictor variables because it's just too many columns. Remember, the more predictors I have, the more prone to overfitting I am. And so here, this gives us a nice reduction in dimension. All right, so the first time I taught this class, it was in 2020, and this was right before COVID kicked off. I mean, right before the world shut down, and the Democratic primaries were going, but we hadn't had like the full dropping out yet, and so I'm still using their tweets. I've used this data set a few times for other examples, and so I'm going to go ahead and load my data, get their tweets. And then I'm going to use my quick way, since we've already talked about the prepping our data. I'm not going to put a lot of time into it. This is my fast, quick, dirty way to get ugly things out of tweets, get non-word characters out, or non-printable is actually the term. I'm getting rid of numbers, and then I'm getting rid of excess space. So this is just a real fast, dirty way. The model is not going to be that great as an output, but you can at least see like where to go. Remember, your text analytics data prep can make or break your project by a lot on this. All right, so you're putting everything to lowercase, removing stop words. And then I'm just removing things specific. Microsoft Word displayed these characters funny. So this is not actually what was in the data set. And there were some misspelled words, and so some things I looked at. So, this is a presidential primary tweets. And so in my point of view, there's no difference between America and American. Even though American would be a person, America is a country. For the purpose of political tweets, I view them as the same. And here, this is something from the formatting of tweets. And I replaced real Donald Trump with just Donald Trump. Also, Trump, this was from a formatting of the tweets. And then, once again, I interpreted presidential and president to be the same thing. So there were two different words for president. It's like presidential and president were different. So I just said they were the same thing for this purpose. Because usually when this one was coming up is because they were criticizing President Trump. All right, so now stemming the words just makes everything have a consistent presentation. So if I have jumping, jump, jumps, jumper, it's all the same. Presidential, presidency, president, all get compressed into the same, presid, be the same. Now, on this, after I stem the documents, these are not going to be actual words that we see going on in my documents. And so if I was going to proceed where I was going to present this to like people outside of my data office, I would need to do the stem completion step. Stem completion can take a long time. On the laptop I was using, it takes a really long time, so I didn't do it. And so now here I am taking the tweets, converting this to a vector source in the TM package. And so this is a vector to get the corpus going. It needs to be a vector source, just something particular about the TM package. And V corpus stands for volatile corpus. And so there's regular corpus, which is intended to not be tinkered with, not to be manipulated. Volatile corpus is intended to be still messed with. And so honestly, all the functions will work the same, but it just works a little bit better if I'm going to actually be messing with things to deal with the volatile corpus. And so at this point, I'm going to create my document term matrix off of the corpus, and then I'm going to remove any terms that have 95% or more. If I have 95% or more zeros in the column, I'm going to get rid of it. But my document term matrix, so I'm setting it up so it's going to be counts. Another approach I could have done is instead of counts, I could go in and change it so that if it's greater than 0, it's a 1. If it's 0, it's 0. I like by default to leave it as the counts. Times that you would prefer zeros or ones is when you would have highly skewed values. If all of a sudden, so let's say that I've got all my documents, I've got maybe some tweets, maybe some books, full books, tweets, Facebook posts, something like that, where I have an inconsistent number of words, or you're just offer the opportunity to have more repetition, like the books numbers will just be proportionally too big. To keep it coherent, I could go through and make sure it's just zeros and ones. All right, now something that I find very frustrating about corpus, volatile corpus and regular corpus, is that it's hard to just look at what you have. And we have a special function for that, the inspect function. And this gives me a quick look at what's going on. So it tells me, here's the number of tweets I've got going on. After removing, so remember I removed stop words and I went to common stems. So common stems means that I have less variety in my words. Then I remove sparse words that only appear in in a few of the tweets. So after that's all done, I'm down to just 64 words are in there. Now, take a look at what we have here. What do we notice about this? They're all stop words. Yeah. For some reason, it did not run. And yet you can see it's there, it's don't know how. So on my computer, when I was running it each time, line by line, it was working. But when I hit the run to make the document, something about our markdown isn't run. But that's what I've got, and the laptop that this was computed on, it just took a long time, so I never updated it. But conceptually, this will still carry through, that we can see how to do this. All right, so now after I'm all done with, after I've created the document term matrix, there are some rows that have no terms. And so, there's some inflammatory tweets that only had a few sparse words, or only had stop words, or they only had symbols in there, or maybe a website, maybe an email address, and all those got stripped out. And so those rows do nothing for me. And so I go ahead and I remove tweets that have no terms in them. To do that, I'm using an apply function. So first margin means that's rows. Remember, rows before columns. 1 is rows, 2 is columns. And so if the sum is equal to 0, it's getting dropped out. So I'm saying keep the ones where it's greater than 0. And you notice I'm filtering the tweets and the document term matrix. All right, so now what we're going to do is we're going to use a latent Dirichlet allocation model with 5 topics. And 5 was just, I just played around with it, seems like a reasonable way to go. And so what the latent Dirichlet allocation model is, all right, so when you see Dirichlet, this is, in statistics, almost the only way we have from a math point of view, having a mathematically complete point of view of random probability vectors. And so if we were to take, let's say, a length 5 probability vector, if we were to take 5 gamma distribution random variables and then rescale them by the sum of the 5. So the first entry gets divided by the sum of the 5. The second entry gets divided by the sum of the 5. The third gets divided by the sum of the 5, and so on. Then what would happen is that each individual entry would, as long as we have the same shape scale parameter on the gammas, each individual entry would end up being a beta distribution, and altogether, the vector itself is called a Dirichlet distribution. So the reason why you will see this over and over and over really is because it's mathematically complete. Like we can have, it has a structure to it that from a math proofs point of view, we can sink our teeth into it. Potentially, we could take any, non-negative numbers, random numbers, and have a probability vector. But, we want to be able to have a more complete point of view to have better inference. We don't really, and the gamma distribution is flexible enough on this, on the shape parameter, that we can, usually get what we would truly want off of this. And so we're going to go with a latent Dirichlet allocation model. So what we're going to say is that the null hypothesis is that the probability distribution of the probability, or the probability distribution of the likelihood vectors for the likelihood of belonging to each of the 5 topics is in fact Dirichlet. All right, so let's go ahead and do that. Let's do our LDA model. So here are my tweets. Notice that this is my document term matrix going into there. Here's the number of topics I'm interested in. I'm saving it here. And so now, when you do this in real life, you're going to explore different number of topics. You're going to look at 2 topics, 3 topics, 4 topics, and so on until you feel satisfied with what you got. So once I get my topics, and so that's what I did when removing stop words works. I played around with it, and I concluded that 5 was about right. 6 was too few, 4 was too many. So how did I reach that conclusion? I looked at exactly what we're looking at here, and I just looked at the words down this list for each of these topics. If it looks like the words are coming together overall to form like a coherent grouping of words, then I say, hey, that's a topic. So at the time, this is a presidential, competition. They were talking about like one of the topics was over healthcare. And, you saw, Medicare, you saw, healthcare prices, hospitals, doctors, words like that were all in one topic. Another one, a topic was of gun control. And so, words that were connected towards, gun control issues were all in another topic. And environment was one. That one was probably the least of the tweeted topics. And then, there were two more. But if you thought about presidential debates, you could anticipate what the five were. They were all pretty easy to spot. When I went with 6 topics, I felt like there were words that were like overlapping too much. I saw them in multiple columns more than I should have, and therefore I thought, that 6 was too many. So when you have too few topics, what you'll see is it looks like you have words from 2 or more different topics going on. And so, until you start seeing them like separate out better, just keep on growing it. If you don't know, go with too few topics and too many. Just like in statistics, anywhere else, you always want to go with a simpler model. A simpler model is better than a more complicated one of equal informative value. All right, so next thing we can look at is how much did each term contribute to each topic? All right, so to pull this out, we need to use a special function. So I dropped my latent Dirichlet allocation model into the posterior function. And so you'll notice that here I've got each of the words. I've got the 5 topics, and you can see how much each of these contributed. I've got 64 different columns going on. There's a whole bunch of them. And we can use this to help identify where individual terms land in terms of topics, if we want. So like here, about a stop word, we can see that it looks like, 5, 2, and 3 are relatively large, for the word about. And if we went with America is probably in topic 5. Now they all kind of land in, they all go somewhere, and you can see that they can contribute to multiple topics at the same time. All right, so now that all of this is for the individual terms. And so that's using the posterior function. We can also look at the topics themselves. All right, so here, if I look across this is going to be a probability vector, row-wise. And so this is my modeled likelihood vector that an individual topic or an individual document belongs to a particular topic. And so here we're seeing that about 0.2 across the board for each of these. Now realize that this didn't run very well because I did not remove the stop words, but you can, so in this particular case, I've got almost all stop words like left. It's a horribly polluted output. And what do we see as the conclusion off of it? Every document is about equal in each of them. So it's a crap model, it's a junk model, but you can at least see potentially that if this was a larger value, I could go, hey, document 1 belongs to, topic 2. And you'll notice like 2 and 3, 3 is going to be one of those rows that had no words after I filtered out. And so, that kind of gives you an idea of how much how many rows were lost. So another thing that would be of interest is, do we have correlation between topics? All right, so if I have correlation between topics, what that's saying is that either the words are appearing simultaneously at the same time, or they're not. They could, like if one topic's coming up, the other one is not, or it could be that they're overlapping with each other. And so if I see a strong negative correlation, then that, if one's counts are going up, then the other one's counts are going down. They're completely separate. But realistically, in politics, things bleed over with each other. You can't divorce one topic from another. And so it's worth it to go through and take a look and see, like, where do we have correlations? So 0.41, that's probably bigger than random. 0.44. And so now if I use the terms, and this is how I find, this is how I usually like to identify what each topic is actually talking about, is the terms function, is that I go through and I just look and see, do we see like a pattern? Do we see what's going on with each of these? And I read the words, and very quickly, we usually pick it up. All right, so how many topics should we use? So there's no good hard firm answer with this. Just like with any other aspect of dimension reduction, we haven't found something solid that is, a magic way to determine the number of topics. So your model will change. So notice I'm saying not might, it will change. Your model, your output will change if I change the number of topics. This is different from PCA. With principal component analysis, if I go with 3 or I go with 5, the first 3 are going to be the same regardless, up to a sign change. But when I'm using non-negative matrix factorization, the number of topics changes because I'm changing the rank of the matrices in that product. And so we can use perplexity and likelihood, the log likelihood of the model, to kind of give us an idea of how many topics to use. And so one thing that we could do is we could go with a lower perplexity for the intention of having a simpler model. All right, so now, here we have the log likelihood of the model. See the degrees of freedom. Here is the perplexity. Now, so just to get an idea of what's going on, I'm going to go through, I'm going to run lapply. So remember, anytime I want to do a for loop in R, I probably don't actually want to use a for loop. I want to use lapply or sapply. For the numbers 2 through 20, I'm going to take that number of topics. I'm going to rerun this topic modeling all over again. And then I'm going to get a list of latent Dirichlet allocation models. Once I'm done with that, I'm going to drop all 19 latent Dirichlet models into the log likelihood function and then plot to see what's going on. And so we can see the log likelihood decreases as we get more and more topics. Now I can do the same for perplexity. I already have established the model for each number of topics. And we see the perplexity grows. And so here, this was more interesting in the original version. Any questions about this? All right, so why do we do this? What is the goal of topic modeling?
To identify specific topics and like social network or something.
Yeah, like what are people talking about? You know, yeah, so we identify, if we know the topics, we know what they're talking about without having to actually read all the documents, which I find that interesting. The idea that I could go in, do text analytics, I know what you're talking about, even though I didn't read, more than a few entries. All right, so we could do topic identification. Another reason would be if I want to see how much each individual document contributes to a topic, or classification. So so for classification, we could see, hey, I think this one is topic 1, this is topic 2, this is topic 5, this is topic 3, and so on. The other one is I could try and use my likelihood vector to identify multiple topic documents or single topic documents. Any questions about this?
If I have, for instance, a huge amount of documents and I was trying to classify them, like for injustice in judicial cases, we have different kind of cases, different petitions for each type of case. So I would use this approach to try to classify them and to send them to specific servants to deal with them.
So that possible. So if you wanted to, have different people handling different topics. So let's say let's say I have 5 writers that need to cover, okay, how about let's think about the legal situation where people will make a public records request, and in response they'll get a whole bunch of printed out documents, and then the lawyers have to go through individually and read through it. And so, they'll get thousands upon thousands upon thousands of binders of documents. And when the defendant is trying to be an ass and slow things down. So what you could do, scan all the documents, then, all right, I've got 6 people who are going to have to wade through all of this. Do topic analysis for 6 topics. And then you have to classify, all right, you get this batch, you get that batch, you get this batch, and you get this. That way they're all, they're able to form more of a narrative of what's going on because you've broken it up. That would be an interesting way to use that. I would enjoy being part of a legal team for that. So off of what you said, I could also see using clustering, using k-means on the document term matrix would also work. It just depends on what your goals are, and how you want to proceed. But definitely would make sense to me.
I work for the judiciary, so
okay.
We have cases. Usually they are classified. They have a class specific, and they have some subjects, specific topics. And usually the lawyers they don't attribute the correct topic to what they're doing. So the judges they ask us to classify first information so that they know exactly what they're dealing with. And depending on the topic, you have a more or less complex case.
So let's say you want to automate this. You would take in I assume they file this electronically. They file it electronically. You strip out the keywords because the keywords are wrong. You take the body of the text, you run through this process, then you classify it. And yeah, so you would take a bunch of old documents, strip out the metadata, strip out the keywords, take the body of the text, do topic modeling, get your LDA model. Then when there's a new filing, you pass that filing through the LDA using the same data prep you used on the original documents. And then you go, okay, this is probably this. I'll take a look at it, but I'm anticipating it's going to be like this way. The man-hour time could just be a cursory look, or you could just look and like, oh, they got the keywords right. And the keywords match the LDA model. I won't even read it. And that way, that would reduce the burden on the staff. Yeah, I would enjoy working on that project. Good question. All right, so now let's talk about sentiment analysis. All right, because of Zoom, I can't quite see. Give me a moment. Oh, Zoom is literally blocking. I don't think you can see this on those of you who are watching on Zoom. There we go. That's what I want to do. All right, now we want to talk about sentiment analysis. So this is in the current issue of Significance for the American Statistical Association's monthly publication. They're talking about using social media posts to check for like mental health and using sentiment analysis to do this. All right, so the goal here is that I want to take a document and I want to classify it in terms of like happy, sad, angry, and so on, or maybe just positive, negative. And so there's different ways to approach sentiment. One is just positive, negative. The other one is to be more specific in like the emotional aspect of it. Now, why would we want to do this? Well, let's say you're working for a large company and it's a huge company. Well, when there is something bad posted on social media, is that good for the company? No. Now, if you're talking about a huge company, nobody can just truly monitor what's being posted for them. There's enough posts, enough topic about them. So what you could do is, in an automated manner, scrape out the tweets, or the Facebook posts, or whatever social media, whatever posts are about your company, and the social media platforms will definitely let you pay for this. You take that, run sentiment analysis. If it's heavily negative, that's an opportunity to reach out and go, hi, we see that you're unhappy. Could we do something to make this right? Another possibility is like, hey, I see that you put in a really great post. Let's go ahead and post that on our website as what are people saying about my products? And so when it's a positive, you can grab it and say, hey, this is what people are saying. This is an honest testimonial. When it's negative, that's an opportunity for you to address a problem. And sentiment analysis can do this in an automated manner for us. So that way we don't have to have people manually doing this. All right, so for sentiment analysis on this one, I'm just going with Biden and Trump. So at this point, Biden, when I pulled the data, Biden had locked down the nomination. And so, we're just talking about the two, candidates for president. And here I'm pulling in the data. There are CSVs. I'm using Lapply. Notice I'm using Lapply to not as quickly as possible, but pretty quick, get two different files loaded. Then I'm using dplyr to put it into one data frame. It is actually a tibble. And then I am reducing it just to the part that I want. So I'm going with the author and the actual text of the tweets. Now I'm doing my data cleaning. This is my quick, fast, dirty way to get rid of ugliness in tweets. converting to consistent lowercase, and just cleaning up the stuff that I know. All this is just copy and paste of the previous. All right, so now, one thing that will have a big impact on how we, on the output of our model, is how we approach sentiment. All right, so when I say sentiment, this particular one analyzes anger, anticipation, disgust, fear, joy, sadness, surprise, and trust. These are the individual sentiments. And then positive and negative is going to be the sum of the positive ones and the negative ones. And so there's going to be 4 positives and 4 negatives, if I remember correctly. So let's see. Anger, disgust, fear, sadness are negative. And then anticipation, joy, surprise, and trust are positive. And so here we have the positive counts that got pushed over because there's only so much real estate in our markdown. All right, so now my goal here is on this analysis, I want to compare the 2 candidates in terms of positive and negative sentiments. And I just want to know, what are they doing? So this is their tweets. That's from their campaign. So I'm going to take the counts I've got in here. So this is the sentiment counts. What has happened? This function went through and it found all the words that it has in an anger list and gave a count of the number of times that there's an angry word, number of times that there's an anticipation word, number of times that there's a disgust, fear, joy, and so on. Now I'm going to split up the data by the author. So I'm going to have a sub data set of President Trump and a sub data set of, at the time, Vice President Biden. All right, so now, why do I do this? You'll know why do I do this split instead of another way of extracting. Something that I highly recommend when you are working professionally with data is you keep similar objects in terms of similar structure, the same structure, put it all into one list if conceptually it's like the same, functionally the same thing. So this way, what I've got here, I'll be able to iterate everything I do, I can iterate over that list very quickly. If I would imagine I had all those candidates for the Democratic primary, and I had an individual data set for each one. Well, in that case, I'm gonna have to, manually put in my code over and over and over to be able to work over it. If I have everything in one clean list, I can just, drop it into sapply, lapply, for loop, and boom, I've got it. And so now, what I'm going to do is I want to know about their overall sentiments. So I want to know how often is President Trump using an anger word? How often is Vice President Biden using an anticipation word? And so on. And so to do that, I chose to use column sums. Now, I could have converted this over into zeros and ones also, if I just wanted to know there is anger in this tweet, there is joy in this tweet, there is trust in this tweet, and so on. So now this will give me the column sums. And so now I want to look for the difference. That's really what I want more than anything, is I want to see that contrast between these 2 candidates. So what I'm going to do is I'm going to sort on the difference of the 2. So here I have the column sums. I want to know what is the difference in the counts for the number of words. Here I'm sorting because I want to see that difference. I want to see that contrast. And then here's the names on it. And then I'm making this into a data frame where I have the screen name, and then I have the sentiments, and then I have their counts, And now the string is factors equals false. This makes sure that this data frame, my string data stays strings instead of factors. All right, so now let's go ahead and actually look at the plots. All right, so when I look at this, so it's been clipped off, but here's negative, disgust, sadness, anger, fear, surprise, joy, trust, anticipation, and positive. All right, so what do we see for the difference in them? Where is the difference negligible?
Pretty much everywhere except maybe positive.
Yeah, except for
Everything else is pretty close.
Yeah, yeah. So here, so there is a little bit of a difference. So my eyes, I feel like there is, there's enough of a difference to say there is a difference. It's not huge, which, yeah, trust. So like both of these are kind of like the same borderline difference. Anticipation and positive, we're seeing the difference. We see, disgust, I would go far enough to say that disgust is a difference, but I don't say you're wrong. I just see it just a little bit differently. But definitely sadness, anger, fear, surprise, these are all about the same. So negative, disgust, and let's say, well, proportionally, it's probably lower count. So let's go ahead and say joy, trust, anticipation, and positive. There is a difference. All right, so which candidate uses more negative words overall? Yeah, Trump. So it's, now what about for positive? Yeah, Biden. And so he's using, and specifically, he's using more joy, trust, and anticipation than specifically than his opponents. While most of the difference here is, if we look at the difference in the red, we can see that disgust. So overall for negative, they're about the same except for disgust, where President Trump uses more disgust words. Is that kind of interesting? Like, does this tell us something about the candidate as a person or as a candidate for the job? Unfortunately, this got clipped off. If you run the code in RStudio, this looks a lot better. And I feel like in the proper version of this in RStudio, if I was using this for work, I would save this as a PNG file using ggSave, and then I would copy or I would drag that PNG into the PowerPoint slide. That's usually how I found is a really good way to go. PNG looks so much better. This looks pixelated. This looks like crap, right? You don't want to show this at work. You want it to look crisp. You don't want anybody to think it's like old looking. But something I want to point out is you'll notice I've got three things going on for the visualization. I have geometry, and I've got the actual value labeled on there, right? And I have color. So the color corresponds to the standard colors for like the news and politics. I've got the number, so that way if a person doesn't like geometry, they like the heart, they prefer reading actual numbers, it's there. And I've got the geometry so that those of us who are more comfortable with bar plots can look and see the difference quickly. And so I find that this is a winning combination. Also, notice that I set this at an angle. So something that will happen when you're doing your plots in real life, when you have the longer names, either I could go through and shorten that, but I wanted to keep it to the actual author to be consistent. My choices are to change this or put this at an angle. At some point, if you're doing enough visualization, you're going to have a long name you're stuck with. This 45-degree angle, I feel like, is a good way to break it up. All right, so now another sentiment analysis package we can use is QDAP. So there's a lot of QDAP and corresponding shoot off packages, so, such as QDAP dictionaries, QDAP regular expressions, QDAP tools. There's, you know, there's a lot of utility in this range. All right, so what I want to do, I want to get the polarity of the individual texts. All right, so polarity is going to be positive and negative for like the sentiment, for the polarity of it. And so positive, it's a positive sentiment, negative is a negative sentiment. And so here, when I go with Vice President Biden and President Trump, you can see the total number of sentences, total number of words, average polarity, and the standard deviation of the polarity. So what do we gather off of just looking at that? And here's the standard mean polarity. When I look here, is that much of a difference? If I was to do a t-test, could I kind of use what's on the board to figure out what's up? Yeah, so if I was to take the difference, square root of this squared divided by n, this squared divided by n, I could get an idea of, in terms of a t-test, is there a statistical difference? But just looking at the average polarity by itself, the raw numbers, what do we conclude off of these two compared to each other? Yeah, they're opposite. Which one's more positive? President Biden and President Trump is more negative. All right, so which is consistent with the previous analysis, right? Yeah, but you know, this is a different package, different function. So this is going to be a different measurement. So it's like if I was to measure athleticism by how much you can lift, or measure athleticism by how fast you can run, you know, you could get differences if you have different athletes, but you know, for most people, you'll be concluding, you know, athletic, yes or no, will get the same result regardless.
Dr. Smith.
All right, so here we can look at the polarity of all of them as a group, get the summary. And so we can see here's the mean, median, quartiles, and we've got missing values in there. And so this is probably from tweets that after all the cleaning out, there's no words that are polarizing. And so here is a visualization of their tweets, positive or negative. So if I see a dark blue, that means, so it's bad to be reusing colors, by the way. That's not something I'd want to do if I was doing this professionally. But so this corresponds to like the, you know, sentences as we go through the words, and we see, you know, we can look and see if there's a pattern. So where this would be useful is if I was trying to use this to spot somebody having depression or maybe a manic phase. If I was to look through, let's say manic depressive, during the depressed phase, we can see a lot of blue. Manic phase, we see red. If we see like a string of red dashes and a string of blue, string of red, and so on, then that could, you know, give us an indication of something like that. And that's the kind of thing that the Significance Journal is talking about in this month's issue. And so now, if I look here, this is a you know, this is like a scatter plot where using jitter. So this is the polarity of individual tweets, but you can see that there's a lot of points. Since there's a lot of points, like overlapping, what it does is that puts a jitter aspect to kind of wiggle it vertically. And so all the points on this line actually are on one straight line. But since there's overlap, to kind of give us a sign of like how many are actually there, it's wiggling it up and down with a jitter aspect, with a random number generator. And so we can see, here is, the individual values. Here is going to be so that will be the mean of it. Here's the mean. We can see a slight difference. And so this can give us an idea of what we have for the polarity of their tweets. And so now let's create a data frame where I have the author, I have the polarity, and I want to go ahead and do a plot. And so now I can get a histogram of the tweets. All right, so when I look at this, histogram, what does this tell us?
Higher concentration of polarity for President Biden.
Yeah, so Biden has this peak here. And so because of this peak, we can see that's where his increased, positivity is coming in this region. All right, what about this split? I mean, is this a typical distribution that we see? How often do you see a distribution like this in a theoretical statistics class? Not too often. All right. So what's going on is that we can see that very few tweets are like neutral. Either they're they're positive or they're negative. There is no like middle ground. Like the purpose of the tweet is either to be super positive or super negative. Does that sound like something a political candidate would do? What would we expect to see if I told you it was a positive topic? A positive sentiment tweet, what would we expect the topic to be?
Good things about the
Yeah, good things about themselves, right? Now, what if it's negative? They're trash talking. They're trash talking. So all of this, we can see like how much trash talking is going on. Now, something I kind of find interesting is that when it's President Biden being positive, this is really not that far to the right. So it's a little bit positive, but it's not like crazy far, it's not a lot farther than the rest. All right, so some alternative sources for sentiment words. If you go in and you search the net, you can find just a lot of people have worked on this. This is a sexy topic in data right now. It's fun. I enjoy this. So the AFIN package, how this one approaches is that it gives a magnitude of positive and negative values. So we can see that like the word abandon is a -2, while abhor is a -3 in its variations. And so the other packages, it was all or nothing. It was 0 or 1 in terms of a sentiment. Now, here it's a little bit more nuanced. And we can see, this gives us the ability to kind of get more interest into it. Now, if I want to go in RC, what this does, this gives us another way of classifying different words. So this takes all these words and classifies them. And you'll notice that abandoned is simultaneously anger, fear, negative, and sadness. Now here is for the sentiment for Bing, and this is just going positive and negative. And each of these sentiments will give us a different model, different output, different inference, but all kind of interesting. So it depends on what you're doing. It depends on your project, what output would be best. And, you can explore all of them and see the one that works for your project. Any questions about this?
Dr. Smith.
All right, then we will get to our last topic of the night, which is string distances. All right, I'm just gonna close this. All right, it's fine. Simple Chrome. All right, for this portion of week's material, we want to talk about string distances, string metrics. Now, you're going to hear me say metric frequently. Technically, it's not actually a metric from mathematics. A metric has to have it's zero. We have to have the triangle inequality symmetric, and it's only itself can have a distance of 0. Technically, triangle inequality can fail on what we're looking at, so it won't be a true distance. It will be a metric. So when I say distance, it's not a true mathematics distance. It is just a metric measurement. Now, but we don't need to really worry about that. So what we want to be able to do, we want to be able to say some kind of, like, these two words are close to each other or these two words are far apart. Well, why would this be useful? Well, what if we wanted to do a spell correct system for us? Like, we wanted to manually build spell correct. Well, when I have a misspelled word, a word that's not in my dictionary, I would want to go and find a word that is in the dictionary that's close to it. If something in my dictionary is close to it, it's more likely to be what the person intended to spell. Also, where I have personally used this, I was in a situation where I had 2 data sets. I did not have ID numbers. Actually, I did have ID numbers. I matched ID numbers on the ones that on the individuals that matched, and then I was done. But I was in a situation that the client did not want to lose one data point. Because of legal reasons, they could not lose one row of data. If they lost one row of data, potentially somebody from the state government could, during an audit, say, what's up with this individual row? And then they're in trouble. So I matched everybody that I could, as much as I could, off of the ID numbers. And the ID numbers were, they believed to be reliable. I took everybody without ID numbers or without a reliable ID number. And then I needed to merge by names. Okay, well, some people, their names matched up very nicely. It was there wasn't a problem, but it got a little bit trickier. Think about the situation where you have Elizabeth on one data set and they have Beth on the other. Or maybe somebody has a hyphenated last name and they switch the order of the hyphenation on the other data sets. Or maybe they only put one of the 2 hyphens. Maybe they put their middle name. All of these are things that can come up, and all these did come up. And so my first go at this with just the raw names, I was using string distance, but I found very quickly that it wasn't accurate enough when I went in and started looking at individual cases to make sure that my technique was sufficient. To make sure that I did better matching, what I did was first, I grouped by birthday. And then I did string distance. And then at that point, that was close enough that the client accepted the matching. And then on the two data sets, there were still some in, on the left data set, some that were in the right that weren't in the other. But it was a small enough list that the client could do things manually. But there was some issues, still some problems. So I was matching on name and I was matching on birth date, but it still wasn't good enough. It wasn't quite, it was almost good enough. Any idea where the problem would be? If I was trying to match people in two different data sets by name and birthday. Almost. Not duplicates. But almost do. If you talk about people, what's almost a duplicate?
It's not unheard of to have the same
Yeah. Yeah. So you could have this, like my name is Aaron Smith. Okay, you can look up Aaron Smith on the internet. There's tons of us. I'm the best looking one, but that wasn't actually a problem. It did occur, but it was such a low rate that the client accepted it. Twins. All right, so
when you say that, you're talking about identical, I guess twin. I guess it doesn't matter, maternal, paternal, where they have their birth,
Yeah.
it's like minute off.
yeah, they have the same date of birth. Now, in terms of string distance, they have very close names. That was a situation I could not beat. Because I'm limited to two spreadsheets. Everything I've got are in two data tables. Everything is like effectively two spreadsheets. There's no way for me to tell if this person's a twin off of what I had. What I found, and I did not realize people did this, is that they will slightly change the name, the legal name of their twins. So like, one is Jason with an E instead of an O. One is, let's say like the name Aaron, one's the name Aaron with a hyphen or an apostrophe, or literally just an apostrophe on the end of the name was one of the cases. And the twins was if the parents gave them nearly the same name, it was that was problematic.
Somebody used like Eric with a C and Eric with a K.
Yes, that's exactly it. Eric with a C and Eric with a K, and they're twins. That's not confusing at all. But if they're kids, they can do what they want. It's just my job to work on this. So the moral of the story is you need to individually check rows of your data when you go through a project like this. So in string distancing, I'm using strings, I'm using character strings, like a person's name to match on records instead of an ID variable. And highly useful, a powerful tool for certain situations, but you have to know of this problem. So if this is a situation that could have like legal ramifications, if there's a mistake, like you need to make sure that it's a very unpolluted output. And you might have to just tell the client, I can't do this. Or maybe I have it down to a short list. This is what I think it is. Somebody needs to manually check, but I at least have got it down to a short list for you. All right, so we're going to use the string dist package. I love this package. I've seen this used in genetic research and pharmaceutical modeling research and vaccine research also at Georgia Tech. So we want to compute the distance between two individual character strings. We want to compute the distance between all entries of a character vector. And we also want to be able to find the best match between two character vectors. So this is a situation where I'm trying to do a match merge. And so I'm in a situation where I can't trust the ID numbers I have. So first and foremost, when I've used this for matching, when I had ID numbers and I trusted them, I took those rows of data and I did the matching and put those off to the side, the ones that matched. Everything that didn't match, or I just didn't trust the ID numbers, because like, let's say they had temporary ID numbers instead of permanent ID numbers. If they only had temporary ones, there was a prefix that indicated it was a temporary one, so I knew I couldn't trust it. And all the other ones, I started doing string distance matching. All right, so first one, we're going to talk about, really there's three major groups. We're going to talk about the DIST ones first. The reason why I talk about these first are these are the simpler ones. These are, from my experience, these are not the best options, but these are easier to understand and easier to kind of wrap our heads around. So when I say dist, all right, so this should be delete. Our operations are delete, insert, substitution, transposition. All right, so if I wanted to convert the name Janie into Jane, that is one operation. If I delete the Y, then the name Janie becomes Jane. And so what we're going to do, we're going to count the number of operations it takes to make one word into another word. Or in the string dist package, here are the different ones that we've got. In the dist group, we have Hamming distance, which we only use substitution. We have longest common substring. The longest common substring is equivalent to deletion and insertion. Levishstein's distance, and this is the like default way for a lot of ones to work with. And this is delete, insert, and substitution. Optimal string alignment is doing deletion, insertion, and then transposition once. So deletion is I go in and I delete a letter. Insert is where I put it in. Then substitution is where I take it and I replace it, which you could also get by deletion and insertion. But deletion and insertion would be two operations. Substitution is one. And then transposition is changing the order. So like if I want to make Eric with a C into Eric with a K, that could be one substitution, or it could be delete the end letter and then insert, either way. And so now these are the dist distances. These ones here, which we'll talk about in a moment, are the Q-gram distances. And the Q-gram distances take matches of substrings to figure out which ones match up. And these all are based off of the Q-gram distance. It's kind of like the fundamental way, and these are all variations of that. Then the last one, SoundX, this one is used, what this does is takes the word, converts it over to phonics. And once it's converted into phonics, it takes a distance between the phonics characters. All right, so at one point when I was working with these, I went through and on the particular data set I was working on, with the known cases, I took my known cases where I had those correct ID numbers that I knew that I could trust, and I ran each of these distances for matching to see how well they performed. For that particular spreadsheet problem, longest common substring gave the most accurate, then Levishstein's distance, optimal string alignment, then full Devereux Levishstein's distance, then cosine, Q-gram, Jacquard, and Jaro-Wilks with P equals 0, then Hamming, and then SoundX. Now, something I need to point out about SoundX, or excuse me, about Hamming. Hamming only allows substitution. All right, so my name is Aaron, 5 letters. The distance from Aaron to Eric, 4 letters, is infinite under the Hamming distance. Hamming distance, I can only substitute. So if you start with 5 letters, you end with 5 letters. You start with 4 letters, you end with 4 letters. So since I can't delete or insert, if I need more letters, I can't get it. So if there's a different number of letters, it's automatically infinite. So if you're in the situation where if 2 words have different number of letters, like you trust the number of letters for matching up, then hamming is a good choice for that. So the Jaro-Wilker distances, what these do, these run the q-gram distance, but then applies it's mathematically modified and puts on a penalty on there. And cosine is basically the angle between the vectors. It's like you can think of it as correlation. All right, so now the string dist function, this goes through and this figures out the distance from one string to the other. And here I'm just copying and pasting from the package, honestly. CA to ABC. All right, if I wanted to make CA into ABC, how could I do that? This switch the order and then insert one. All right, so switching the order is a transposition. The default string dist method up here does not have transposition. So therefore it's going to be 3. Because so there, how this gets converted into the other, let's just say delete C, add B, add C. So delete, insert, insert would give us 3. And so now, if I want to figure out the distance between different things, if I ran this, this would give me a 4x4 matrix of distances. This will give me a 3x2 matrix of distances. I notice I didn't print this one. If I want to change the method that I use, I just change the method. And that works for any of these functions. It's always method every single time is the keyword. And now something that is important, notice here. All caps and all lowercase, caps and lowercase are different. But if I go to 2 lower, we'll notice, boom, it's the same. So if it's 0, they're the same. We can also do a weighted version. So in the default setting, deletion, insertion, substitution, and transposition all have a weight of 1. If I wanted to change that, here, deletion, insertion, substitution, transposition, we're saying transposition has half the weight. And so we can change the weighting of it. And here it's just like playing around with it. Oh, now something about that, if I use, you notice I just have an H, this is for hamming. So in this package, I don't need to spell out the whole thing. I just need a unique term. So like I couldn't do just J. I can't use just J, but I could go JW. I could go JA. If I do a distinct prefix aspect of the word, like L is not good enough, but LV is. So I don't have to spell out the whole thing on it. The package will run. Here's longest common substring. Now when I use qgram, I need to specify like a penalty parameter, or no, sorry, that's length of substrings. Qgrams, I need length of substrings. And you'll notice that these are different, but they are in fact string distance of 0. All right, what's going on is that I'm saying break these up into length 1 substrings. So I have A by itself, B by itself, C by itself. Here I get C by itself, B by itself, A by itself, but order doesn't matter. Since I have the same substrings exactly, it's a string distance of 0. But you'll notice now, if I go with length 2, what we're going to have AB, we're going to have BC, we'll have CA, and we'll have BA. And you notice that none of those match. And we end up having a string distance of 4. And this is Q grams with a penalty term. Here I'm changing the penalty. So here, remember, a distance gives me a measure of dissimilarity. If I change it over to, and this one is bounded between 0 and 1. If I change it to 1 minus the distance, that can be a measure of similarity. So a correlation is a measure of similarity. 1 minus the correlation squared could be a measure of distance between vectors. Now here's an interesting one. Euler and Gauss. Now here I'm going off of the phonics of it. So a good time to use SoundX is if I had so like right now, you can see that there is a transcript that's being generated. It's taking my words, making it into text. Now, if you want to match up that to some other document, since this is kind of the machine is picking up what I'm saying, it's converting it to phonics and converting that over to words. SoundX would be a good choice if I wanted to run string distance on the text that's being generated right now. And here's Euler and how do you say this? Ellery. And how do you say this? Euler. It's Euler. Yeah, but you'll notice that string dist gets it wrong. Yeah, if you're a math major, you'll know. I'll say that you'll mess this up one time, and your math professor will jump all over you. I know personally.
I've read that.
Yeah. We also do similarities. So we do pairwise string similarities between elements of the vectors. Now here in this situation, if I have different length vectors, it's going to use vector recycling. So it's going to repeat entries to get equal length. Get things to work. You can see that here Martha and Mathra are nearly 100% equal to each other. Here I'm measuring similarity, not distance. Conceptually, very related. Now the A match function. The A match function is for approximate matching. So this is where I'm trying to go through and do that merging off of approximately the same words. So words that maybe I misspelled here had correct, I'm trying to match them up. I'm trying to find the pair. And so here, when we do this, and the default is LV, I say a maximum distance is 5. So in this situation, I'm saying, hey, find a match, but only if the difference is so far out. You'll notice that if the difference is too large, it'll give me a missing value. And so here, on this one, we're going to take Leah and Uhara, and we're going to try among Ripley, Leela, Scully, and Trinity. What is Trinity from? I know the rest. Is that Matrix? So Star Wars, Star Trek, Aliens, Futurama, X-Files, The Matrix? Yeah, I think that's right. All right, so Leia, we can see is matching up with Leela, second entry, but Uhura is not matching up with any of these because the distance aspect is saying, hey, if it's beyond a certain distance, don't go with it. Now, one problem with this, think about the name Tom and the name Anne. Are those similar names? No. Now, how many operations would it take to get Tom into Anne? To use deletion, insertion, substitution, transposition? It would be 3, right? Now, if we're talking about longer names, you know, like 2 longer names, let's say somebody with like a 10, letters, and somebody else with 10 letters. A distance of 3 would be pretty close, right? Well, so in this system, max distance of 3 with longer words, with longer names, that, max distance of 3, like we're really confident that these are matching up. But when we deal with names like Tom and Bob, the short words, this isn't really that great of a way to go. Now, if I want to absolutely 100% get a match, like find me a match somewhere, put the maximum distance to infinite. And here I just specify if there's no match, don't give me missing value, give me 0. The AN is just to approximately, is this in there? So approximately is Leia and Uhura Leela. And it's going to be true. And, we can keep working on that, change it up. And so the phonics function, what this does for us, this does that under the hood step of converting the words to its phonic representation. So that just so we can see what is it if I want to work with the phonics themselves. And so we just drop that in to get that. Now with Q-grams, so here I want to manually show you how Q-grams actually runs. And so here I have hello world, and I want length, sublength 3, HEL, I have LLO, this is LO space for here. This is space, or O space W. ORL, RLD, and then L, and then space WO. So something to notice is that if I have a space or a punctuation character, that is kept in there. So it's treating that space like it's just any other letter. And when we do the Q-grams, what I really want you to see is how is this getting broken up? It's all of the possible substrings of length 3. Now, if I was to repeat this like that, we can see that by, so this vector is hello world twice. And if I run Q-grams, I can see the count just doubles. And we can run this on each of these. Like that. And if I want, I can run through and run Q-grams on individual strings like this. And where I specify what the row name will be. All these funny phrases are from the help documentation. And you'll notice that this is a character string by itself, and this is a vector of character strings. But I can put them all into one object. I don't have to take the manual step of converting them over. The use names, so you'll notice here that I've got A, B, and C on my row names. If I say use names equals false, it won't do that for me. And it will drop the column name. So if I just want the counts as a vector by themselves, well, it's actually a row matrix. I can do that. Any questions about this? All right, so can we think of some applications for this? Like, when would we want to use string distance?
Spell check. I guess it is.
Yeah, spell check. So like Google, when you mistype something, or Google thinks that there's something else, they're running a string distance. Probably the most common example is when you meant to type in one thing into Google and you get something else.
Be maybe kind of a stupid thing, could you build like an anagram solver out of something like this?
Yeah. So if you were to, yeah, so let's say I had a dictionary of words. So imagine like the only valid words are the words in the Scrabble dictionary, let's say. And I have the word, I could run string dist. Let's run qgrams of length 1 to find the matches, and boom, we've got it. Yeah. So on that one, you're matching, since you're doing anagrams, your matching would have to be perfect matches. But if you have an entire dictionary, you've got something. So yeah. So if you wanted to cheat, let's say you're playing an anagram game on the computer against people, and you take the word, type it in real quickly, you get the results, and then you type it in as fast as you can. You're on the computer, and you cheat like that. I think Boggle does this.
Yeah, something like that. Or you could cheat a tree if you wanted to.
Yeah. Yeah. I think Boggle might. You could use string dist to cheat at Boggle.
Okay.
Yeah. Once it's been a long time, but I one evening I just tried the game online, and there was somebody who was just beating the snot out of everybody by like a large amount. I think they were cheating, but I didn't know how. And at the time, I didn't know about string distances. So yeah. Any questions? All right. So what did we go over this evening?
A lot of ways to extract, run some kind of analytics on text.
Yeah. Okay. So the first topic was topic analysis. Yeah, topic modeling. Then second one, sentiment analysis, and last one,
String.
all right. Now, what would be an application of topic modeling?
This is one I only saw, or I couldn't really follow it. Your examples make sense, but I was like, how the hell else could you use this?
Yeah. Yeah, text classification. So yeah, also if you had a good topic modeling, and I kind of envision it as like, I don't feel like reading this entire book. Could I get like topic modeling to just tell me like the big topics of it, so I could take a test without having to read.
Maybe it's like a similarity recommender, right? Like
Yeah.
if you like this book, you might.
Yeah. You definitely could do that. What about sentiment analysis? Where could we use where could we take advantage of sentiment analysis?
Any sort of reviewing for products.
Yeah. So if we see positive, we want to do what?
Like sell more.
Yeah. So someone puts out positive stuff there, we can target them for advertising. I didn't think of that one. That's a good one. Yeah, if someone's putting negative comments, I'm not gonna waste my time on them. Also, if there's, if you're talking about like customer service, and you have like a positive, negative sentiment about somebody coming in, maybe it's like, all right, they're negative sentiments, person has a history of being difficult, let's go ahead and like put them last in the queue. And like a person who's gonna be like friendly and quick and easy to take care of, put them high up. I know of a company actually doing that, by the way. I'm not gonna say who.
So they know that if someone's in colossal pain, they'll like, your Q position is 17.
Yeah,
Your
yeah.
Q position is 10.
Yeah, exactly, exactly. They'll get farther in the line. Well, if they're a client you want to drop, you know, like insurance companies legally can't reject people, but that doesn't mean they have to do things to keep them either. You know, that's good. And that's one like all profitable insurance companies do, is that if they don't have to go the extra mile for someone they don't want on the books, you know. And so string distance, can we think of a use of string distance? Yeah, spell check. The way that the biggest one I want you to keep in your back pocket on this one, and you don't have to remember how to do it after this class, but remember that you can use this if I need a match on names. If you have to match on text fields that you don't trust to match. In the situation that I don't trust the ID numbers, or maybe people have gotten temporary ID numbers and not permanent ID numbers, or ID numbers are just absent. And I have to match on names or some other text field, then, this can be a way to go.
Like data script, like, or if you're trying to clean your data, right?
Yeah.
Or standardize that kind of process. You could run it through some of this, not just matching individual patterns, but like, if you've got a corpus that you can't really examine. And
Yeah.
use this to actually find issues.
Yes. Yeah, there are a lot of uses, but it's, I think it doesn't come to our mind as quickly as other ways. And I know of one researcher at Georgia Tech that's using this for vaccines, like to actually, take information about the virus, the target virus, and like the protein sequencing, and represent the proteins as a string of characters. And then the idea is use the information in there to see, like, would this vaccine work? Yes or no, without having to actually run clinical trials. So to try and get fewer unproductive trials going. Any questions? All right, then if there's nothing else, let's call it a night.